Okay, shall we resume?
Yes.
Okay. Okay, so probably let's try to solve it. So we should calculate the total number. No, let's say there are n people in the group, right? And then we actually, the actual question is about n, right? It's about number of people in the group, but let's, for the moment, just assume that there is n people and calculate the total number of possible, say, combinations of birth dates. And then somehow we should distinguish those combinations where there is at least two people that have birth on the same day, maybe more than two people. Okay. So it's actually, no, at least total, for total number is easy, right? So we have n people, we have 365 possible dates. I don't count this, how it's called, високосный год. So let's say there are 365 possibilities for each person, n persons. So we have how much? How much possibilities? N person, so many options for each person, right? So, okay, let n be the number of people in the group, right? For each person, there are 365 options when this person may have birthday. Options, right? So total number of options for n people. We already had that in many situations. Okay, if n equals 2, say simple case, right? How many possibilities when there's two persons, Bob and Alice, say, when they have birthday? 365 options for Bob, 365 options for Alice, right? So how much in total?
133,225.
Right. So for okay, I believe you. I cannot compute that. I hope you. So for two person, it'll be 265 times 365, right? Because so many options for Bob, so many options for Alice, and if you have n people, what it gives us total, say, number of options. No, I just say total number, okay? So for 2 people, it will be this 365 square, and for n people,
365 in the power of n.
right? Exactly, right. And that's maybe depends on n, but it may be quite a big number, right? If n is big. Okay. Now we should distinguish among this total number, right? Those where there are repeating birthdays. So how we do this? If any one of you. This actually is not so easy, right? Because we may have just 2 people the same birthday, we may have 3 people, and even n people all born the same day, right? So that's kind of complicated. All right. No, okay, I can give you a hint. So hint is, and calculate not this number, but rather the complement. So the number of options where there is no repeating birthdays, and that's much easier, right? Let's call that we'll say S for sum, right? It will be this, and now we want to calculate, say, well, let me call it something like NR, for example. No repetition, all are different, right? So how we calculate this? When there is no repeating birthdays. Now that's the same pattern we already seen so many times. So
Factorial? 300.
yeah, it has something to do with factorial. It's not 365 factorial though, right? Because we also should somehow take this n into account, right? But that's so suppose we have this n people, right? Take 1 person, and then there are 365 options for 1 person, right? No restriction. But then we are talking about second person, say that was Alice, and for Bob, we already have 1 less option, right? So Alice has birthday certain day, and we don't want that Bob has his birthday on the same day as Alice, right? Say this is for Alice. Okay. Now, so for Bob, it's B364, right? 1 less. And what about their friends?
$363 and
yes, and then of course it depends of n, right? So it's times so should be n factors, right? So product should be of n numbers beginning. We had the same when we counted number of arrangements or number of combinations, but I'm not going to use this formula. It's just the same pattern, right? So should be kind of head of 5 factorial, but we should take a head of this. So we should divide by by what? We should somehow to kill this tail. So what is the last factor here? It will be, so this 365, 5, this 355 minus 1, minus 2, and finally it should be minus n, but then plus 1. You see why plus 1? Because we didn't count here. So this is minus 1, this is minus 2, and it's actually minus n minus 1, because we should also count this first factor, right? Or otherwise, we can actually write this down also in that way. So we should divide it by 365 minus n factorial. So we may also write it in that way, or simply in this way. So let's say that way. So that's a right number. You see why? Yeah. So that's the number of combinations, or how you call it, possibilities, where there is no repeating birthdays. No repeating birthdays. And actually, the trick is repeating birthdays. And the trick is that that is easier to calculate, easier than this number that we ask for when there are some repeating. So it's easier to calculate no repeating birthdays. And then what we want actually is that is S n R over S be what? Be smaller than 1/2, right? So here we calculated when there is no repeating birthday, right? And that means that repeating birthday would be chances for repeating birthday would be more than 1/2. If no repeating birthday, less than 1/2. And that's, of course, a calculation. So basically what we want to calculate, let me write it down again, is this. No, let me write in this form, minus n factorial, and then I should divide also by this number, right, by s. So I should write it here. And you see, it's all rather, even with relatively small n, those rather big numbers, and yeah, it's, you would rather need to write a short program or something. It's difficult to calculate. So we should calculate it for different, no, let me call it, say, ratio, or C for chances, right? And that depends of n, of course, right? It's a function of n. So we should calculate it for different n and look when, well, it's clear that what that number it decreases, because if we have right, if we have more than 365 people, say 366, all right, it's not even possible that all have different birthdays, right? Because we have only 365. It's, by the way, it's called in mathematics Dirichlet principle or pigeonhole principles. So if we have, say, 300 pigeonhole, because if we have 365, say, holes, right, and we try to fill them with 366 items, then necessarily in a certain hole will be more than two or more items, right? We cannot just arrange it in a way that each item will be in its own hole, right? So it's clear that if we take n big enough, that number will be small. Actually, if we take n, here we get 0, right? Here we have 1, and then what? So we should somehow get what? We should get actually 0. Oh. But we don't get 0, right? So if we have no, right, that's because you see here our formula actually break, because n can be bigger than 365. Why not? We have a bigger group, but we didn't calculate it for like negative factorial, so we should then apply some different kind of reasoning, right? However, if n just equals then yeah, sorry, a bit difficult, a bit confused how this formula behaves. Right, because that's we calculated. Right, that's we calculated situation when. Sorry. So that's calculate when there is no repetition, and that's simply not possible if we have exactly. If we have. No, it's okay. So if n is equal number of years in a year, right? Then we still may have a situation, of course, when all dates are different, right? Right. It's kind of small, but it's non-zero, and we calculate that exactly. In that case, we have this factorial divided by that's power to n, and this is kind of small number, but it's not 0, of course. And what happens when n is actually bigger than 365, then you see our theory doesn't apply. That's also, by the way, interesting. You see, we kind of modeled our theory, our problem with our formulas, but actually we should specify that that reasoning simply works, that n is smaller or equal than 365. And if it's bigger than 365, right, then we simply should use, then we don't know what is a factorial of negative number, so all this reasoning doesn't work. However, there is another simple argument of this pigeonhole principle. It just says that if n is bigger, then it's 0 chance that all dates will be different. But it's not seen immediately from our formula. It's you see requires different reasoning. Yeah, that's what happened. However, if here we get 0, if n equals to 365, then it's okay. Then we get some small chance that they still have different birthday. Okay. Yeah, now, of course, I would ask you to compute all of this. However, let me show other people did it for us. Can you see PDF now?
Yes.
Right. So so that's how this function behaves. You see, it's called. This is our n in the left column, and that's the outcome. So if there is 10 people, it's a lot of chances that all birthdays will be different. It's like 88%, right? If there are 20 people, then it's a bit more than 1/2. However, I think the crucial number, for some reason I can see here. Yeah, here the more precise calculation. So you see, it's when 22 is a bit more than 1/2, still a bit more. But if it's 23, it's become less. And this is a result of calculation. It's not something you can really, how to say, get otherwise. You need to compute. No, it's not really heavy computation, of course, right? It's all can be done with the calculator. However, yeah. And I don't, so the right answer is 23, right? When there are 23 people, then there are more than half chances that will be 2 persons born on the same day. And that's, I don't know, it's kind of surprises many people. I don't know, it seems you surprising or not surprising, because it looks kind of small number, right? You have 23 people, you have 365 days, right? Which is like 20 times or 30 times even more. No, not 30 times. Not even like 15 times, right? And so you kind of intuitively, but erroneously, that's if it is indeed someone intuition, it's erroneous. It somehow suggests that the number of people should be kind of comparable with the number of days in the year. Should be some kind of 300 people or something, but in fact, you see the number is much less than that. So if you have a, I don't know, group of 30 people, for example, there is a very good chance to have people born on the same day. And you see, if you have 100 people, that's kind of almost sure that's at least 2 people are born on the same day. So it's very low probability that for otherwise. That's, yeah. That's, well, that's kind of a standard problem or puzzle, if you like, or whatever. Okay. Yeah. No, okay, maybe last thing I wanted to show you for combinatorics, but there will be more problem. I'll give you a test with problems, and so it'll be just exercises, and then also a test, and we'll also look together into tests. And problems are different. Some problems are kind of stupid. You can simply apply given formula, but many problems like this one, right? They are less trivial, less stupid. So you should really think a little bit. You still use patterns, and patterns are not many of reasoning, but you should really think how to apply them. Yeah, that's how it works. Okay, so so last thing I wanted to show, it's called for some reason it's actually popular in Russian. It's called бином Ньютона. Слышали, наверное? Это что-то из 19 века, из какой-то гимназической практики. Кто-нибудь знает, что это? I think it's written binom, yeah, that way. No. And does anybody know who is Newton? No?
Yes.
Yeah. Newton is no. Sometimes, actually, I think in school he mentioned in a course of physics, right? However, in fact, he was no, he was both. He was physicist and mathematician, and he was really a great mathematician who invented just completely new parts of mathematics, is what we call mathematical analysis, this differential integrational calculus. But actually he invented many things, and that is known for him. So what this binom, you certainly learned in school, I think we already came across, that sort of identity, a plus b, so we have a sum square, right? So if we extend it, so we get x square plus 2ab plus b square, right? Probably you know, at least in my school education, we had it. What would happen if instead of square we get a cube? So what happened with the cube? Does anybody remember? So actually, yeah, you can just multiply.
A
Nobody?
square plus 3
No,
multiply.
not square. It will be cube, right?
Q, sorry. A cube plus 3 multiply x square, or a square b
Yeah.
plus 3 multiply a b square
Yeah.
plus b cube.
Cube. You see, the total power each time is 3. So here we have square and power 1, right? So the total power of this моном, it's officially called. По-русски это как-то одночлен, называлось, да? Моном in English. So the whole thing called polynom, многочлен. Polynom. And that's is called monom. And monom has power. Okay. Yeah, that's fine. Remember, what would happen if we have 4? Say, and actually any n. And that's what calls Newton binom. So. No, of course, that we can do kind of routinely, just multiplying, say, this by one more AB. No, maybe one time we can do this, right? So with that, we should multiply once again by A and by B, right? So it's, say, the same as a plus b cube and times a plus b. Well, let's do this as a little routine exercise. So it's be a4, right? Just to see how it works. A4, then, so first that's all just multiplied by a. So it's 3a cube b, right, plus 3a square b square plus ab square ab cube, right? That we multiplied by a, and now we multiply by b, so it's be a cube b, right, plus 3a square b square plus 3 AB cube, right? And plus B power 4. And now we should what? We should add what we can add. So let's see. We have AB cube, for example, here, right? And we have 3AB cube here. We can sum them up. And we have 3A cube B. Let me just underline red. And we have A cube B here. And otherwise, we can do anything, right? So it's going to be A4 plus 4 times, this time 4 times, all right? That plus that, A cube B. So that stands as it was. No, I'm sorry, not as it was, because we have, say, here and there, right? Plus 6 A square B square plus 4 again A B cube and plus B power 4. Yeah, what we got. Yeah. Now we can probably see the pattern how it works, right? As I say, all these monomes, they have this total power 4. So in case of n, for example, it's clear it would be A to n on the left. It will be B to n, and it's symmetric. You see, whatever we have. So we may swap n and B, and it would remain the same. No, obviously, because this formula is also symmetric, because A plus B is the same as B plus A. It comes down to that. All right. Then we have all things of kind of n minus 1b plus, say, n minus 2 b square, etc. Right? Then we have a n minus k bk, right? And here we have a b n minus 1, right? And so what actually, no, you see, it's symmetric in that sense, just as this simple formula. So what remains, yeah, here will be no coefficient, because say if you have this many brackets, you just multiply a by a by a, so this will always remain without any coefficient. No, otherwise saying coefficient is 1, like here, right? So there is no coefficient. However, at these places, no, I will put this interrogation sign just to, there are some coefficients which we want to somehow to find out what they are, right? So in first I can write like a table. So here it was just 2, right? In so that's for this formula. Then we had 3 and 3, and there we had 3 sorry, 4 6 4. So we had 6 and 4. All right. And by the way, you see that kind of pattern that 3 plus 3 gives us 6. However, that gives, and to get 4, we actually, I think, should just add 1. But okay, let's That's has a name. It's called Pascal. I think he Pascal Triangle. I think I did not reproduce the normal way. Reproduce it. I just begin with this, like with 3 ones, and then I make 2, which is sum of these ones, and then I add 1, and I get this 3, and the same. Yeah, I add 1, I get 3, and then I again add 1, and here I get 4, here I get 6, here I get 4. No, it's now it's you see, it looks a little bit like little magic, but then it is actually a way to obtain these coefficients. But let's actually think. Let's as you say, it's kind of combinatorial thing, right? It's combinatorial in which sense? Let's me probably make a new picture. So what we have a lot of these monoms, or like this times, let's write it once again, and then times and a plus b. Okay, and we have its n times. Now, how we multiply it, right? How we extend it? Say we take a, for example, right, or b. You see, we have 2 options. Now, let's say we take a, and then we have again 2 options. We may either multiply a by a or multiply a by b. And every time we have such 2 options. But the problem is, of course, that when we do this, sorry, something stupid, previous, yeah, when we do need, you see, we obtain actually homogeneous, по-русски в школе, по-моему, называли, у нас в школе, по крайней мере, однородные члены, homogeneous elements, right? Like here, that we should add, and so we should somehow calculate how it works. Yeah, and that's actually where combinatorics comes in. So basically, what we want to calculate, right? We have, say, this monomial form a to n minus k, b to k, right? And by the way, we may also observe that it's all symmetric, right? So we have 3 here, 3 there. We have 4 here, 4 there. No, as I already told, that's something to expect. So we may probably, no, let me just denote for the moment, this coefficient denote that way. So it would be, I think our notation like this, nk, right? So I have 2 parameters, and it's actually be the same as coefficient with say a to k and b n minus k, right? Where k is a smaller or equal, right? Maybe equal. No, it's smaller than n. Right. So here I may say that this thing would be equal to Cn n minus k. That's something to observe. Right. But now let's think what kind of combinatorics is involved. What kind of combinatorics? Right. How we get, say this this thing. So we have n times okay, let's just say how it's possible that we have the same products, how we can get the same products, right? Yeah, so each time we choose either A or B, what we want to use as a factor, right? Either A or B. And so at the end, what we have that we, and we are making n choices, okay, in total. But these n choices, they consist actually of choosing, let's better look at that part, that we choose A k times, and what remains, we choose B. So it's B k times, and but that's already automatic, so to speak, right? If we've chosen A k in times, then it follows that we choose B n minus k times. Yeah, but that I'm talking about this series of choices that just so let me describe the process in that way, right? Each time I choose one of these, and I'm making n choices, and k times I choose A. So I have a total number of my choices. It's 2 to n, right? So I have 2 choices every time, and choices. No, it's not actually quite relevant. But what is relevant is among these 2 to n possibilities, how many are there possibilities such that A is chosen k times, where k smaller than n. Right. And that's something we discussed actually last week, even if under different words. Remember, we have like n items, and we want to take out from these n items k items. So what it was, how it was called, I don't know. You were given like 10 items, the distinguishable, and you want to take out 3. How many possibilities for that? How we? And you see here the same situation. We have n choices, right? There are certain choices among those such that A is chosen k times. And question is how many are such things? And then we should sum them up, right? I'm sorry, do you follow? Or someone is lost?
Yes, we follow.
You follow. You remember we were talking about number of arrangements, and number of arrangements was then the same situation. We have n items, and then certain k smaller than n, right? Say n 10k equals 3, for example. An arrangement was how we choose, say 10 letters, how many words of 3 letters of this alphabet of 10 without repetitions, right? And that what we denoted like a number of arrangements. I think I was confused where to put n, where to put k. I think we put k here on the top, right? And on the bottom. No, I think it's actually, I'm not sure that there is standard version. Somehow I will also oscillate, right? But that was easy. That's something we just a minute ago we came across, right? Basically what we need is n factorial over n minus k factorial, right? But then we also introduced what we call the number of combinations. And what is the difference between arrangements and combinations is that in arrangement, the order matters. So say if we chosen, say A, B, C, right? Then B, C, A, it's a different choice. However, in other situation, when we simply have, say, 10 objects and want to take out 3 objects, and there is no order in which these 3 objects are arranged, you see? Then we called it number of combinations. And so we divided that because, again, number of combinations is smaller, right? These 2 different arrangements, they count as the same combinations, like different arrangements, but the same combination. Because we're simply saying, okay, we have, say, 10 letters, and we've chosen these A, B, C, and we don't put them in any particular order. And that's we called combination. So for each, so then to calculate it, we just took number of arrangements, which I rewrite in that way. And then we had to divide it by number of permutation in each arrangement, right? So that was also k factorial here, just to identify, if you like, all these permutations. And so that's exactly what we need here, you see. Exactly because the multiplication is commutative, so it's not really important in which order we get our summands, right? However, just what is important, how many they are. So again, n choices and how many ways to choose a k times. And that's exactly that number. You see? So, no, if you like, it's a theorem. So let me call it Newton's theorem. Even I'm not sure if that's really Newton discovered it. Could be discovered earlier, but could be, I didn't check actually. But somehow he's known for that. So a plus b to n. So we got kind of a general formula is this is a to n, and here we have b to n, so it's symmetric, right? But here we have c, so I put that down, n 1 plus c n 2, sorry, I forgot this. So here I have a n minus 1b, okay, plus c n 2 a n minus 2b, b square. I write down. Plus. So somewhere in the middle, we would have something like Cn to k, right? A n minus k, b to k, right? And then it just goes symmetrically. So we also have, right, in the middle, no, where it's the middle actually depends of n, probably. So certain point we may have, but it actually depends. If we have a even, if n is even, will be something like a to n to 2 to b to n to 2, right? If it's odd, we'll not have such a thing. Okay, so it's okay. It's not essential, but what is essential that we would have also for b kind of symmetrical thing, and this is n minus k here, right? And a k b n minus k. So you see, k plus n minus k equal k. So the total power is always n plus what? Okay, let me write this. So it will be sorry, n. Here is we have always n. Here we have say 1, like here, right? But here a b n minus 1 plus b to n. Yeah, that's. No, you see, it's a lot of formulas. However, the essence is simple. And somehow in 19th century, your predecessors learned it. Right, so that these coefficients, which are really problematic, right? Because what's going on with these monarms is clear. But what is less clear, what are these coefficients? And as we've shown, these coefficients, actually, they are given by these formulas with combinations, right? And it's also something we did observe earlier, and maybe it's a good way to observe it, is exactly that. That's no, already let me write it down again. That this is symmetric. So we can write down that this is actually equal to that. So that's interesting identity. No, if we write down formulas, it's actually clear. Let me do that. So it's n factorial over n minus k factorial and the k factorial, right? That's, I calculated this left part. And now if I calculate by the same pattern right part, it will be again n factorials always, but what we get in denominator, instead of k, we have n minus k, right? Instead of this k, so we have n minus k factorial. And here we should do n minus k and n minus and instead of k we have that, right? n minus k, and this is just k, right? So we get k factorial, we get the same, you see. Yeah. No, yeah, so that's kind of piece of knowledge. I don't know, maybe I don't think you really need this formula. You need, but I think it's nice combinatorial example. It's nice application, if you like, of combinatorics to algebra, and also somehow people in 17th century where Newton lived, they figure it out how it works. So it's not very complicated. And last thing, but here maybe I'm not sure I give you a proof, but okay, I just go back because I shown. So Pascal, Blaise Pascal, he's also French philosopher and mathematician. Sometimes he's credited for inventing probability theory. So he was kind of gambler. He invented a mathematical theory of gambling, which was new. But he also showed this kind of diagrammatical way how these numbers can be computed, you see. So instead of computing these factorials, you do this diagram. No, it's not, it's actually kind of an algorithmic question, right? I think it works well with human mind, that, as I already mentioned, we do well with diagrams, right? If you try to write a program, it's actually less clear. I didn't try myself. It's less clear whether that really gives you advantage, but it's not impossible, actually. Yeah. No, maybe it's good questions. Why, right? How, why by just doing this mechanical thing, we obtain these combinations after all, right? Well, actually, if you think it's this procedure is kind of similar to what's going on here. Let me try to say how it's similar. It's actually you see the pattern, right? You should just sum up what is above on the above line, and you add one always, right? And so you just compute it line by line. All this sometimes they're also called binomial coefficients, binomiальные коэффициенты, exactly for Newton, right? So yeah, I think if you just follow different paths from top to down, right? This following these paths somehow models also this procedure of extending the binomial, right? But yeah, no, probably will not now spend a lot of time with that, but it's very well known and also nice thing. Yeah, probably that was it with the combinatorics. And no, except there are more questions. So of course, it's as I told you, there is rather serious disciplines. There are really complicated theorems of that. But what I showed you is very elementary, but there are also very basic and I think very useful. I know if there are some questions about this part, and we'll have more problems. I'm going to send you also problems with this. Not now. This Microsoft Team. Yeah, don't hesitate to ask me. No, okay, if there is no questions, actually, new topic. I think we'll we have some 20 minutes left, so we started. So you somehow have certain idea what is about, and next time we elaborate on it. Okay, so I think it's kind of related, not directly, but anything. So it's called numeration systems. Huh? Okay, what is numeration system? Actually, it's how we express, how we denote numbers. No, just using kind of I could call it syntax for numbers. Actually, if I asking you what are numbers, right? What kind of number? No, you probably told me, you would tell me that, yeah, it's kind of 1, 2, 3, etc. No, as I already mentioned, actually, there are, of course, like fractions, also 1/3. There are also some strange numbers like square root of 2. We already came across. There are even more strange numbers like pi. But for the moment, we leave that aside. No, even I would say a couple of things about, actually about all of this. Also, we talk about numerations. No, however, if you just try to answer naively, you would say it's something like 3, 5, 7. If I ask what to do with numbers, you can say sum up 5 and 7, it would give you 12, right? And things like that. However, what I want to do now is somehow distinguish. You see, here actually certain alphabet is used, right? How many characters is in this alphabet? I mean, for denoting numbers, right? How many characters? Or symbols?
9.
10, right? So we have this. Yeah, 0 is important. It's actually more theoretic concept already, right? It's not in natural numbers, but actually it's very important for notation, because that's kind of notation that we use. It simply cannot work without 0, right? For example, we know that 102 and 12 are two different numbers, right? And what makes them different syntactically is exactly this symbol 0. So, right, it's or you say 1 and 10. It's all different. It's a very important symbol, and it plays a very special role. Yeah, but otherwise we have 10 symbols. There is some story behind this, that actually it was invented by Indian mathematicians And then certain Arab mathematicians in Middle Ages, they learned it, they translated this kind of treaty into Arabic language. Then people already in Europe translated this Arabic manuscript into Latin, and that's how they learn it. And you know, that was in Europe. Yeah, so that's our 10 symbols. They, by the way, in India, they had different versions, so it's stabilized only lately. So there are, of course, the same symbols could just be used for something else. Say, for example, right? So it took a time to stabilize this syntax. However, it's relatively late. I guess it was very beginning of process was some like 12th century, right? There are some books I can recommend where you can find better information, where just this kind of knowledge came to Europe. You know, one reason was that it was not at all in the center, so to speak, of European mathematics, and European mathematics is actually inherited this classical Greek mathematics via Roman Empire. And in Greek mathematics, if we take like Euclid, I already mentioned it, right? Euclid's Elements, there is a book on arithmetic, but there is no, there is nothing on numeration system. There is nothing about notation, because apparently Euclid, and actually it was not a personal attitude, it was kind of very strong cultural thing, that they did think this question is important. You see, they believe this kind of question is for trade, for something. Actually, what they did use for trade, and the same, by the way, was in old Russia at a certain point. They just used Greek alphabet, gamma, delta, epsilon, etc. Right? They put something like a prime, and that meant that that was a 1, 2, 3, right? 4. But then they came to 9. I don't remember exactly which. They took the other part of the alphabet, something like mu, nu, omicron, p, rho, right? And now I can't remember. I should check. But imagine that nu may mean something like 20. You see, so this. No, actually, we can just look for. Okay, we are not in the hurry. I just try to Greek alphabet. Yeah. So if we have somewhere, yeah. Yeah, so here we have a Greek alphabet. Now I should share screen. All right, let's take this, for example. Okay, can you see it, right?
Yes.
Yeah, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9. And so kappa is 10, lambda is 20, and the mu is 30. You see? And of course you stop, because say for hundreds, you don't have anything already. You see? So it works just for small number up to roughly 100 or even 99, officially, something like this, right? And then, okay, I think, no, there are books where it's described, they could use some special symbols. I think kind of they reused alpha again. So they, instead of prime, they could write double prime or things like this. But what is important that this system was not positive, and the same was used in all the Russian states. So they as виде, азбуки виде. I think it's So it's just was used for numbers, but it's important. You see that you don't have zero in such a system, and system is not positional. Let me go back to my. So what positional means? But positional means this, that how we know that, say, let me write down 101, right? So we have 100 here, 1 here, and 1 here. But we know it's different ones, right? That's 1 means 100, and that 1 means 1. Okay, so you see the value depends on relative position to other symbols. It's actually interesting. You observe only that we read these things from left to right, right? Because otherwise, if we just read 1, we don't know how many symbols follows, and so we don't know how to compute. So if you have say 2021 now, right? So we should read in that way. So we take 1, okay, then follows 20, but we already 2, sorry, but we already know that it's not 2, but 2 times 10, 20, right? And then it's 0, it's nothing, and then it's 2, actually 1,000, right? So it's 2 to 3. You see? So there is kind of computation and rather involved where the value of symbol depends on its relative position. While in these more primitive systems, it's not positional. So if it was kappa was 10, right? So if I writing like A and kappa, right? So that's supposed to be 11, right? So this 11 may be this way, or I can write it the other way around. It'll be still 11. So there is just 2 symbols, right? Each symbol has a value. We know that kappa has this value 10, and now I'm already tending using this positional thing, right? That we all learned as kids, but people in Europe didn't learn it systematically, I say, until 15th century. Some mathematicians introduced it in 20th century, but it was very limited knowledge, even among people who knew. So it was much later when these things, they became familiar. Yeah. So that's not positional, you see. And of course, probably you know Roman system, Roman numbering, which was used in Europe. That was popular thing, and it's still used, right? So in some places, sometimes just for kind of style, and who knows how it works. So we have just these strokes is simply like units, right? So we have 1 for 1 stroke, 2 strokes for 2, 3 for 3, and yeah, for 4 actually there are 2 versions. There are sometimes 4, and sometimes anyway for 5 there is it's like a palm, like ладошка. 5. Of course, it all goes back to fingers, right? We should also ask what is so special about number 10, because you see 10 plays a special role here. We have 10 symbols, right? And here when we compute what kind of number denoted by these 4 symbols, by the string 2021. Why it's 2000 something. We also 10 plays a role, so we should somehow know it to decode it, if you like, to calculate. So question is why 10 and not 9 and not 11? No, I think kind of answer is obvious. I guess all of you guess, right? That is anthropomorphic. It's full anthropomorphic that we happen to have 10 fingers on our hands and also 10 toes on our feet, which in some languages also have a trace. In French, for example, for saying 80, does anybody speak French here? No? So in French, for saying 80, you say 80. And that means 4 times 20, right? French system is very complicated. So it's more or less regular. When it comes to 60, you say 60. But for 70, you're already saying 70. It's like 60 plus 10. And for 80, you are saying 80. So you're saying 4 times 20, which is a kind of remnant of certain system when people used to count also to use feet and not only hands. Yeah, that's of course fully anthropomorphic, the things of 10. However, you see here it's positional system with 10, but this Roman system, there also 10 plays a role, but it's not positional. So we have 5. Then yeah, a version for 4 is also this one. So it's like 5 minus 1 that way. Probably you're familiar. Then we have 6, 7, 8, etc. And for 10 we have like 2 pounds. You see. Then who knows what happens? It's actually L for I think 50. It's C for centrum. Centum. This is 100, and this is I forgot. It's something like legion or something. So it's 100. Then I think D for 500, and M for 1,000, right? And then, for example, 2021 will be MM 21, like that. And you see there is no 0. That's a crucial thing. So it is also, we may say 10 plays a special role here, right? So we introduce new symbol when it's power of 10. No, and also when it's half of it also, right? However, it's not positional because usually it's written that way, but if you permute this somehow, no, perhaps it actually depends, better not permute because, for example, to write something like this, you would write, I think, M for 9. I think for 9 you write at least one version. One version of it would be right that way, C and M. So that would be 900. You see, and then you have 50, then you have 60, and then you have 5. Yeah, that's 960, 65. So it's kind of a little bit positional, right? Because that is supposed to Right, and for 9 also that's rather usual thing for 9, right? It's like 10 minus 1, so it's positional in the sense that dependently it's on the left, on the right, it should be either 11 like this or 9 like that, right? Yeah, so it's no, but crucial thing, it's not positional. It's not positional. And actually, you see, for say millions or something, you would need again a new symbol. So with our positional system, we may actually, if we really allow to write very long expressions, right? Of course, in the real world, we cannot write a number of million digits. It does make sense, right? But at least theoretically, we can do with just 10 symbols, right? 10 symbols is enough to write any number if only we don't put any restriction of length of our words. But here it's not only a question of length, but also a question of symbols, because we cannot do better than whatever 4,000 here, right? For 5,000 we would need again another symbol, and so that's different system in that sense, right? Now, so you see, it's rather something that we seems to be in a sense very simple because we all learn it automatically. However, there is a kind of mechanics behind it, and a few things are important. One thing is important to kind of dissociate the syntax from theoretical concept of number, right? We assume that the same number, say 2, we can simply express differently. This is 2 and this is 2, and this is are 2 different words, right? 2 different syntactic expressions, but the same number. So that's very important to dissociate. And also it's important to look how this positional system, or maybe other system, how it really works, right? And for example, in a computer science, important system is not this of base 10, but important is of base actually 2, of 0, 1, so-called binary system. And so what we are going to do next time is to look how to convert from binary to base 10 and otherwise, and generally understand how it works, right? So that's no, you can read something about it. There is a lot of material on the internet, of course, everywhere. It's a popular topic. Yeah, I think I'm going to conclude. So if sorry. Are there any questions?
No.
No, if not, then okay, I'll write you again through, probably I'll give you some exercises for combinatorics. It's important to do exercises. So will be next a test combining, I think, 2 at least combinatorics and this notation system. At least that's how it's written. So it's all, well, in a way, it's similar, maybe not. So okay. So next time we'll maybe also do some more exercises in combinatorics. I'm just repeating homeworks, and then look into this numeration system. And don't hesitate to ask me a question if you don't understand anything. Okay?
Okay.
Yes. Thank you.
Thank you.
Thank you.
Thank
Have a
you.
nice
Thank you.
weekend.
Bye.
So,
Thank you. Bye.
пока-пока.